Welcome to another series solution to an IVP example. So in this example, let's consider the IVP y double prime plus 4y equals 0, with y of 0 equals -3 and y prime of 0 equals 4. Our job is to find the power series solution in X. So this is an IVP that we can obviously just solve using techniques we learned earlier in this course. We're going to go ahead and just practice our series solution techniques and see what happens. And then we can check and see if it matches the actual solution. So note, y double prime plus 4y equals 0 as general solution y equals C1 times cosine of 2x plus C2 times sine of 2x. But we will practice, again, we will practice our series solution techniques. So we will practice our series solution techniques. And see if we get the same answer. And then because we have an IVP, we will be able to figure out our coefficients as well. So let's go ahead and assume that y is equal to the sum from n equals 0 to infinity of a sub n times, in this case, x naught is just 0, so times x to the n. Then we have that y prime as the sum from n equals 1 to infinity of n times a sub n times x to the n minus 1. And y double prime is the sum from n equals 2 to infinity of n times n minus 1 times a sub n times x to the n minus 2. From here, we can go ahead and plug in. So we're going to plugging into y double prime plus 4y equals 0. We get the sum from n equals 2 to infinity of n times n minus 1 times a sub n times x to the n minus 2 plus 4 times the sum from n equals 0 to infinity of a sub n x to the n, and this should add up to equal 0. We can do our shifting of index. So we have a to the n minus 2 in our simplified version. Let's shift that. Let's set k equals to n minus 2. And shifting the index. We are looking at the sum from k equals 0 to infinity of k plus 2 times k plus 1 times a sub k plus 2 times x to the k. I'm going to go ahead and just multiply in that 4. So we have plus the sum from n equals 0 to infinity. 4a sub n x to the n equals 0. Now let's go ahead and rename the index. So renaming the index, we have the sum from n equals 0 to infinity of n plus 2 times n plus 1 times a sub n plus 2 times x to the n plus the sum from n equals 0 to infinity of 4 times a sub n times x to the n should equal 0. Then let's combine the sums. So combining the sums, we have the sum from n equals 0 to infinity of n plus 2 times n plus 1 times a sub n plus 2 plus 4 times a sub n. All of that multiplying x to the n, and then this should equal 0. Then matching the coefficients. We have n plus 2 times n plus 1 times a sub n plus 2 plus 4 times a sub n is equal to 0. And solving for the highest index, so solving for the highest index coefficient, we have a sub n plus 2 is equal to negative 4 over n plus 2 times n plus 1. That whole fraction multiplying a sub n. So now let's go ahead and just solve for a sub n's. So note this n plus 2 being only in terms of a sub n means all the even powers should be written in terms of a sub 0. All the odd powers or all odd coefficients should be written in terms of a sub 1. So we have a recursive formula. We have all odd index. Let's do even first. All even index can be written in terms of a0, and all odd index can be written in terms of a1. So let's go ahead and just sort of figure out what's happening. So note, we have a0, then a2. We would be looking at negative 4 divided by 2 times 1 times a0. A4 would be negative 4 over, we would do n plus 2 would be 4, and n plus 1 would be 3 in this case, because 4 is 2 plus 2. So this one comes from doing n equals 0, and then this is n plus 2. The next one comes from taking n equals 2. 4 is our n plus 2. Right? So in this case, we have negative 4 over 4 times 3. Then multiplying a2. So multiplying negative 4 over 2 times 1. Then this is multiplying a0. Similarly, a6, we would, let me simplify this, sorry. For a4, we are looking at, we have a negative 1 squared. Then we are multiplying by, we have a 4 squared divided by 4 factorial. And then, whoa, I apologize. Then all of that is multiplying a0. If we go for a6, so at this one, we're looking at n equals 3, doing n plus 2. sorry, n equals 4, I'm doing n plus 2. Then we would have negative 4 over 6 times 5, that's n plus 2 and n plus 1. Then this should be multiplying negative 1 squared times 4 squared over 4 factorial we saw before, times a naught. We have one more negative into play. This is negative 1 cubed. Then we have times 4 cubed over 6 factorial times a naught. So we can kind of see a pattern here. It turns out, in general, if we want to find a sub 2k, this is negative 1 to the k, right? 6 was 2 times 3, 4 was 2 times 2. That's the k, that's our power. Then we multiply by 4 to the k. And then we divide by 2k factorial. And then that whole thing is multiplying a0. So you can check this, you can prove it. Often you can kind of see what's happening from the pattern just by doing it. You could do a proof by induction to show this is true. But we do wind up just with this nice product here. So this was for our even coefficients. Now let's go ahead and do our odd index. So whatever our A1 is, A3, we are looking at our original formula, I apologize, was negative 4 over m plus 2 times m plus 1 times an. So we would do negative 4 over, in this case, we're using n equals 1, and here we have n plus 2 gives us 3. So n plus 2 would be 3, n plus 1 is 2. And then we're multiplying by a1. A sub 5, we are looking at negative 4 over, here we should do 5 times 4. Then we're going to multiply that by a sub 3, so negative 4 over 3 times 2 times a1. This we're looking at negative 1 squared times 4 squared over 5 factorial times a1. For 3, we are looking at negative 1 to the first power. A sub 3 would be negative 1 to the first power times 4 to the first power divided by 3 factorial times a1. If we keep going, a7, we would be looking at negative 4 over 7 times 6, multiplying this negative 1 squared times 4 squared over 5 factorial times a1 we found previously. That was just doing our negative 4 over m plus 2 times m plus 1, multiplying by our a5. This simplifies to negative 1 cubed times 4 cubed over 7 factorial times a1. So if we look sort of at what's going on here, in general, if we take a sub 2k plus 1, our standard equation or formula for odd integers, we are looking at negative 1 raised to the k, right? 7 would be 2 times 3 plus 1, so that k would be 3, multiplying 4 to the k divided by 2k plus 1 factorial times a sub 1. What we get then from here we have that y can be split into one piece that does the even terms. So we'll go from k equals 0 to infinity of a sub 2k times x to the 2k. Those are our even terms. Plus the sum from k equals 0 to infinity of a sub 2k plus 1 times x to the 2k plus 1. Substituting in with our new formulas, we're looking at the sum from k equals 0 to infinity of -1 to the k times 4 to the k divided by 2k factorial, then multiplying x to the multiplying by a1 times x to the 2k plus the sum from k equals 0 to infinity of -1 to the k times 4 to the k divided by 2k plus 1 factorial. Sorry, that first one should have been times a0, not times a1. This term will have our times a1, and then times x to the 2k plus 1. I'm going to rearrange this a little bit. We can pull the a0 and a1 out front. So this is a0 times the sum from k equals 0 to infinity of -1 to the k times 4 to the k over 2k factorial times x to the 2k plus a1 times the sum from k equals 0 to infinity of -1 to the k times 4 to the k over 2k plus 1 factorial times x to the 2k plus 1. Oh, I apologize. From here, we have then rearranging a little more. We can throw that 4 to the k inside of our x to the 2k by rewriting it as 2 to the 2k. So we have a0 times the sum from k equals 0 to infinity times -1 to the k times we have 2x raised to the 2k divided by 2k factorial, then plus a1 times the sum from k equals 0 to infinity, -1 to the k. Throwing that 4 to the k inside, we could do it as 2 to the 2k. If we want to the 2k plus 1, we'll need to divide by a 2 as well. So we have a 2x to the 2k plus 1 over 2k plus 1 factorial. But since we did add in an extra power of that, we should also divide by a 2. This is our cosine of 2x, that first sum. The second sum is our sine of 2x. So we do have an answer in cosine 2x and sine of 2x. And then our solution to our IVP. We were told that our y of 0, I apologize for all the scrolling. Y of 0 was -3 and y prime of 0 was 4. So y of 0 is -3. So we know that a0 is -3. Y prime of 0 is 4. So we know a1 is 4. And we therefore get that y of x is simply -3 times the sum from k equals 0 to infinity of -1 to the k times 2x to the 2k over 2k factorial. I apologize, my parentheses got off in that previous one. The factorial applies to the entire 2k. And then we have plus 4 over 2 times the sum from k equals 0 to infinity of -1 to the 2k plus 1. Sorry, -1 to the k times 2x to the 2k plus 1, all divided by 2k plus 1 factorial. So again, this is a rather complicated way to find the solution to an equation we already knew how to solve, but it gives us some practice kind of rewriting the coefficients strictly in terms of a sub 0 instead of in terms of the previous, like the immediate previous coefficients. And this is useful when you want to see, is this a function we're familiar with? But that is solving IVPs using power series.